Hey guys, what's going on? So today we are going to be covering Schwarzschild geodesics. We're going to really bleed out this Schwarzschild metric for a couple of videos because this is the most well-known metric or solution to Einstein's field equations. Keeping in mind that the Schwarzschild metric is, again, a solution of the Einstein field equations. And so with that being said, I hope you guys like this kind of content. Make sure to hit that like and subscribe button. Make sure to go onto my Patreon page if you want to support the channel and or become a member. So now let's get right into it. Alright, so we now have a form of the Schwarzschild metric, and from the metric we can derive the associated differential equations of motion, right? So just keeping in mind again that the metric, so we have Einstein's field equations, right? So the field equations again are, I'm gonna reduce the thickness of my pen here really quick. The G mu nu, this was our Einstein tensor, and then from there we said that there was an equivalence between the geometry of space-time and the mass within that space-time. From there, when we set this guy equal to 0, we effectively get a Schwarzschild solution, right? So this is Schwarzschild solution or metric. All right, and then from there we get G. We can calculate the geodesics. Okay, so we effectively did this part here. We found out, we derived the Schwarzschild metric last time. Now we're going to take a look at the geodesics, and we're going to take a look at them in depth. We're going to see what kind of paths in space-time they predict. And so with that, so let's push on here. So we're starting off with our metric entries, right? So our entries for our metric are the time component, x, y, and z component. There's no crossover terms, no coupling between x and t or z and x or anything like that. This is a flat Schwarzschild metric, and we're going to be doing this in spherical coordinates. And so in spherical coordinates we have something like this, right? So we got this term last time, we got this, and we had this and this here. Now we're writing everything in terms of alpha and rho, right? So where rho is the Schwarzschild radius, alpha is related to the mass, okay? And we want to keep that in mind because we're going to really massage our equation to a point where we can actually find solutions to what our geodesics look like, okay? And so rho again is radius, and the theta, we're keeping just theta, okay? So we're redefining things in terms of alpha and rho, okay? And then we have this theta as well. In order to get the geodesic equations, we need to find the connection coefficients, and we will solve for the temporal geodesics just as an example, and then I'm going to say, do a little bit of hand waving, be like, you can use the same exact method to find the other geodesic equations associated with the other entries of the metric, right? So we have, so we define our affine connection. If you remember, this is our affine connection. We derived this a long time ago. Okay, if you don't remember how to do that and you want to remember how to do that, you can go back to my earlier video where we do this derivation. And then just replacing 0 with t, right, because t is our 0th component to the metric. We get this, and then slimming things down a little bit, here we see that this guy, right, so off diagonal terms are going to be 0, and this here is a temporal component of something that doesn't depend on time, which is the radius, okay? So this is going to go to 0 also, and so we get this guy right here, and that's gonna we have a, right, so this should be negative, right, because of this negative sign, but this is going to give us a 0 nevertheless, so that negative sign doesn't really do anything, okay? And then we have this guy here, right? So this is 0, 0, row, right? So that should be a row. This is a row. And that row is going to be, and so same equation, doing all the same things here, but this time we can actually get a derivative. Wait, my bad here. So this is 0 because of this, right? This off diagonal term. This is going to not be 0, right? Because this is not off diagonal. This is not off diagonal. We can get this right here, and then we can, if you just pause the video, you can look at this and see how I get to here, right? So we're just taking derivative here with respect to row, okay? And so you can sort of see how this is going, right? So GTT, this is GTT, GTT again right here. They have to be inverses of each other, right? So inverses of each other because one is a covariant, the other one's contravariant. And so doing this calculation, we get this, and then so we say that this here is the same as this, which is, we're just reiterating this right here. So this is important for the temporal part of the geodesic, right? So this guy right here, right? Because if we want this to be TT row, right? That's going to be this guy right here, and T and T, right? So this is going to, mu and nu are going to be equal to each other, which is why we have this, right? So we have, they're not equal to each other, right? So this is going to be, we're really just replacing this guy in with the geodesic equation, okay? And then these guys are the temporal geodesics along some parameterized path, right? So the parameterized path, again, is going to be this here. So imagine we have some path, and that path is parameterized by some lambda. What we could probably, we can better represent this pictorially if we have if we write it like this, right? So we have our, actually let's do it like this. We have our manifold, and then our geodesic is some path within our manifold, and so this geodesic is parameterized by lambda. Lambda is the proper time of that geodesic, right? So this could be the proper time tau. We'll just say lambda because it's a little bit more general. But we could just say that this lambda is the proper time, okay? All right, and so what this does, we can do the same procedure, right? So we go through all of this, we calculate all of our geodesic, or all of our affine connections, put them into the geodesic equation, and when we do that, we get 3 more geodesic equations, okay? Each one associated for each of the coordinate parameters, right? So rho is the Schwarzschild radius, theta is the angle of, we have a picture of this later, I think it's right here, right? So we have an angle, and then we have phi, or phi, with theta and phi, right? So depending on how you label these things, one is going to be the angle away from this axis here, the other one's going to be the angle from this axis here, right? And the rho is going to be the Schwarzschild radius, okay? And so we have this equation here is the geodesic for this coordinate, this equation here is the geodesic for this one, and this equation here is the geodesic for this azimuthal coordinate. Okay? And so effectively what we have is we have four geodesic equations, or 4 geodesic equations, and each equation tells us what the curvature is, the double derivative of each one of these coordinates. And notice they're coupled differential equations, right? Because here we have theta, and here we have theta and theta. So these are all coupled with each other, and that's important, right? Because these are all variables that depend on each other. Okay, and that's something to note, right? So rho is dependent on theta, it's dependent on phi. So rho we can think of as a function of time, theta and phi, right? And so we can calculate, for example, d rho d phi, and that's something we're going to do, okay, in this video. And so let's get to that point. So this is all to say, I'm just going to reiterate the point really quick, that we have along some geodesic and Schwarzschild spacetime, then each coordinate changes in a unique way according to the coupled differential equations. These are the coupled differential equations. These are the things we calculated this one, and we use the same exact method to calculate this one, and this one. And in our picture here, here's our geodesic. Here's one of our angles. Here's the other angle, and here is our radius, our Schwarzschild radius. The Schwarzschild radius is really the thing that we're going to be primarily interested in. Okay. So we're going to restrict the conditions such that we're going to be restricted to the equatorial plane here, right? So this equatorial plane. So where this is pi equals theta equals pi over 2, right? So that angle is going to be this right here, right? In this. So we're really restricting ourselves to this plane, okay? And so that's this right here, okay? And when we do that, we can take this equation here, and we notice that cotangent of this is going to give us this, okay? Because this is going to go to 0. And when that goes to 0, we can do a little bit of manipulation. We divide both sides by azimuthal dot, right? So azimuthal dot, and divide both sides by rho, or not. We don't have to divide both sides by rho, right? Because this is just rho dot over rho. So we get this, and then we can see that this is the derivative of a natural logarithm, right? So whenever we see double dot over dot, we should think natural logarithm, and so the derivative of the natural logarithm of this is this. Derivative of rho squared is going to give us this, and this is going to be 0, right? So 0 here, because the derivative of 0 is 0. And so, okay, we could split this up now, right? We can split this up and we can realize, well, the derivative of this is 0. That means this has to be a constant. So here's a constant. And by the rules of the natural logarithms, we get this, which is a constant, right? So nothing changes here. And so what this is saying is that rho dot, or rho squared times azimuthal dot, is a constant, okay? And this is a constant of the motion, right? So this h is constant of the motion. And this is something we want to keep in mind. We can calculate another constant of the motion if and through this way, right? So here's our temporal geodesic. Okay, this is again dt d tau, like that, right? So where tau again is the how we're labeling our geodesic, or the parameter of that defines the geodesic. Okay, and we can do the same thing, right? So the same thing here, tau, or t dot over t, right? So we're just dividing both sides by t dot, And then row, we have the same thing, but we have this alpha, and this should be a row, right? This here should be a row, not an E. And so we get this here. This is all equal to 0. And then same thing here. You have to realize here that the derivative of the ln of this is going to give you this, okay? And I save us a little bit of time in just putting the answer here. You can go through that manipulation if you want, or you can just take my word for it, right? So there's some things that I just did some a little bit of side math. It's really like 3 or 4 lines of basic calculus to understand that the derivative of this will give you this. And then from here we get this guy, and because again we can see that the derivative of this is 0, so that means this inside here has to be a constant. And so we get this here, and this constant is, again, this is just a constant, right? Because the ln of this is the ln of a constant, and that's just a constant. So that means this guy here, this inside the natural logarithm, is a constant, right? It's e to the c, and so e to the c we're just going to derive as called kappa for right now. So this is another constant of the motion. And this constant of the motion is something that we want to keep in mind. So we have 2 constants of the motion. Now let's continue. We can write a line element in the Schwarzschild spacetime in this way, right? This is just G00, G11, G22, and G33. And we can see that when we divide both sides by this guy here, we get the derivative of time with respect to the parameter. We get the derivative of rho with respect to the parameter, and so forth. This guy here goes away, right? Because we restricted it to be a constant. Okay. Doing a little bit more math now, we can see our constants of the motion starting to get play a role in things, right? Because our constant, this guy here, is kappa. So this guy here is going to be kappa times this, right? Because we have this squared. And you can see, you could pause the video right here if you want, and you can see how this kappa fits into this whole term here. This term here, rho dot squared and times all this, well, that doesn't really change because nothing, I don't really change anything there. And then this here, well, you could see how this is related to a constant of the motion as well, right? So this is where h comes into play. So this is where, this point here is really where we're injecting constants of the motion. All right, and then we have this guy here. If just condensing all of this, we get this guy, right? Because rho squared, rho to the 4th, things will cancel. This guy here, nothing changes. And then we can cancel these terms, right? Because we have positive 1 in this exponent and negative 2 in this exponent. So things get condensed, right? And then we can multiply both sides by this thing, and we get this right here. If we move on, zooming in here, we can get to this point, right? Because, so we have this, and it's not terribly difficult to just move things over to one side of the equation, which is what we're doing. And then here we're just expanding, right? So c squared, and then c times alpha over rho, c squared times alpha over rho, is right here, and then c squared kappa squared, c squared kappa squared. Okay, this is a negative because of this right here. All right, and so we can then regroup a few things to get this. We can get a differential equation for the Schwarzschild radius as a function of the azimuthal angle now. And the way we do that, right, so we're keeping this guy in mind really quick, and the way we can calculate this guy now is, well, this guy is defined as d rho d tau, and so we can do the magic of calculus. We can write this in this way, right, because these two guys are the same. And then we get this, right, because d azimuthal by d tau, well, that is d azimuthal by d tau, that's right here, right? Right, so d azimuthal by d tau is this dot, so that's going to be h divided by this, right? So h divided by that. Well, this is interesting now because we're saying that this here is equal to this by means of this. And so what we can do is we can say, well, this here, excuse me, is equal to, let's see here. So we have, let's see, we're putting this into, since this, okay, so since this is this here, and we have this guy here squared, we're going to square this, put it into here, which is this, multiply this by this, which is this by this, which is this, and then we have this, and we have these two guys right here. And then we can do a little bit of, again, canceling and stuff, and we get this guy right here. And lo and behold, we bring things to the other side of the equation, and we can get an equation. This is called the radius anomaly equation, in which we now have the derivative of rho with respect to the azimuthal angle. Okay. So this might seem like I don't know what I was typing here. This seemed like just a fancy, that was supposed to be a fancy equation. I correct myself along the way. A fancy equation. Equation for the arc length, but recall that the radius is allowed to expand in time, so we're not really constricting ourselves to a sphere. The radius anomaly tracks perihelions, right? So I don't know if I'm pronouncing that right, but a perihelion is an elliptical path or an ellipse in which, say for example, the moon rotating around the Earth, the radius here is the distance from the center of each, and the angle is the angle subtended in this way, right? So, and we can get the change in the radius here compared to here as a function of how much the angle has turned. And so, and that function, or the way we calculate that, is through this guy here, right? One way we can look at it also is that this rho, right, so rho isn't this angle, right? Rho is this arrow right here, right? So this blue one, and this radius changes as a function of how the angle away from here. So you can think of, in this picture, the Earth being right here and the moon being here. And so we're allowing the radius to expand as this guy gets larger. So if this guy's larger, our radius might be out here, right? And so that is what this is depicting, this picture is depicting. All right. So these perihelions can be complicated because they're also a function of time, right? And so we can get weird paths that might look like this maybe, right? So we have the weird perihelions that go like this, like, you know, right? So moon might be going in this way, and then it might be going in this way, and then it might be going in this way, and then that whole thing just could rotate in some weird way as a function of time also. So this family of perihelions is therefore governed by two coupled differential equations. This is it as a function of time and how it changes as a function of time, and this is how it changes as a function of the azimuthal, where again our constants of the motion are defined in this way. Alright. Last but not least, we want to get an actual expression, right? Because this here is a differential equation. This is a differential equation that tells us the motion here. What is the solution of rho? What is rho as a function of t and phi? Well, it is, to get that, we do a little bit massaging of this radius anomaly equation. And that massaging, the first step of that massage is going to be right here, right? So we define the radius, we can make this dimensionless through here, right? Because rho is in terms of length. Alpha here is going to be in terms of length also. So if we go back, we see how we defined alpha. We go all the way back up here. Alpha, we said 2m, and in special relativity terms, that is going to be in terms of length. And so to make this dimensionless, we define it in this way, and when we do that, we get this here, right? So we change this guy, and we have to multiply it by alpha to have this be rho, right? So this is what we get when we replace this guy into here. All right. When we redefine the Schwarzschild radius, so this is making it dimensionless. We redefine the Schwarzschild radius in this way, and so in that way we get the derivative, or not the derivative, but a small change in the Schwarzschild radius is going to be this right here. Okay. And so when we redefine the Schwarzschild radius, this is the second step of massaging, if you will. We get this here. Divide everything by rho star to the fourth, and we get this. And then changing things up a little bit, just cleaning things up a little bit. What we said chi was 1 over rho. So we have all these right here, and so this is how we get the chi. So things are looking a little bit simpler now. We can define a stand-in for the mass. So here's alpha, that term alpha we were just talking about. And when we do that, we get this equation, right? So we're just subbing, we're subbing things in, right? So alpha squared divided by h squared is going to be 4s squared, which is where this 4s squared is. Things look really nice now. But now we're going to do one more stand-in for the Schwarzschild radius, which is going to be this u, because chi is the Schwarzschild radius, where we've been consistently saying that we're putting stand-ins for the radius, stand-ins for the radius, so we have one stand-in for the mass. But when we do that, we get this here, and then this can reduce to this guy right here. Okay. Again, I'll just do simple math, right? 4u cubed, and then all of this is just this manipulated, and we have the 16 out here, and so yeah, so you could pause the video if you actually want to get from this step to this step, but again, it's just algebra. It's a bunch of algebra and manipulation of the equation. We know the answer to this equation here, right? So if I just zoom in, this equation here is a differential equation in which its solution is something called the Weierstrass P function. Okay, now if you haven't taken differential equations, this might be a little bit odd to you, but the idea here, the whole premise of differential equations is can we get solutions to differential equations? And a differential equation is an equation in which you have a derivative of some function is equal to the some function, or is equal to some relationship to that same function, right? So a good example would be, say, df dt is equal to f plus d squared f dt squared. This is a differential equation, and we can try to get solutions to that differential equation. So whenever we're presented with a differential equation, the whole point is to try to find the function that satisfies that equation. And so what I'm doing here is just telling you straight up that we actually know what u is to satisfy this differential equation. And u is this right here. And this is another way of saying this is it's equal to this. This is the Weierstrass p function. And there's different ways of writing the Weierstrass p function, but the point here is that we know what the solution to this is. And when we look at this, we see for u, we see G2, this is an invariant, this is just a number. That's going to be this guy, and then G3 is going to be this guy right here. Right, so G2 and G3. And so we can now solve for chi, which is this. And then since chi is the standard for the Schwarzschild radius, we get this here, right? So because remember chi was right here, okay? We define chi in terms of u. And so here chi in terms of u. However, chi in terms of rho, well, we know chi in terms of u. And we know chi in terms of rho star, and we know rho star in terms of rho. So we do all those substitutions, and I'm saving you the time and energy, but this is what you end up getting, right? So this is rho as a function of theta, where this is some function that you can just look up in a table. It's the Weierstrass. I don't know how to spell this guy. So V-E-I, Weierstrass. I think it's S-T-R-A-S-S-P function. And that is this is the geodesic equation. Not the geodesic, right? This is a solution to the geodesic equation for the Schwarzschild. So solution to Schwarzschild geodesic. So solution to Schwarzschild geodesic for the Schwarzschild radius as a function of the azimuthal. Okay, so in other words, we can go back to this picture. If I tell you what the azimuthal angle is, I can calculate what rho is. Okay, so if the azimuthal angle is pi over 2, right, so pi over 2, well, we'll get rho as being this here. Okay, that radius, that Schwarzschild radius. Okay, so we're going to stop here because this was kind of a long video, but the whole point, again, is we're bleeding dry the Schwarzschild metric, because this is something that we're going to really want to hinge our understanding of GR a lot, because we're going to keep on coming back to the Schwarzschild radius or the Schwarzschild metric, because it's going to be very useful in helping us define coordinates, different types of coordinate systems, and more metrics that we're going to solve for. So we're going to again bleed dry the Schwarzschild metric a little bit more, and then we'll get into the Kerr metric. But with that being said, make sure to hit that like and subscribe button. You can also go onto my Patreon page if you want to become a member and support the channel. You can get notes, and you can also become a member. And if you become a member, thank you for that as well. So with that being said, I'll see you guys in the next video.